Hello, my name's Molly Meager, and it's September 18th, 2025, and today I'm going to be going over a combined spectra problem that we were assigned. So, I was given prompt Y, which has the molecular formula C10H14O, and we were given an IR spectra, a CNMR, and an HNMR, and we were told to deduce the structure. So the first thing that I did was calculate the degree of unsaturation, which tells you how many pi bonds you have in your molecular formula. So I calculated that to be 4, telling me that I have 3 pi bonds. So just shove that away for later. And then just to go over the spectra real quickly, IR is used for finding your functional groups. CNMR is used to find your distinct carbon environments, and HNMR is used to find your distinct hydrogen environments. And CNMR can also help you with your bonding as well. So the first thing that I did was kind of just jump right into the IR spectra, see what I could figure out there. I immediately noticed that there wasn't a broad OH stretch right here, around like the 3,000, a little past the 3,000 mark. So that told me we likely weren't working with an alcohol. But I do have an oxygen in my formula. So then I kind of went looking for where that could be, and I ended up landing on a CO stretch right around the 1,200 to 1,000 mark. So that kind of accounts for our oxygen. Moving on, I noticed a very sharp stretch right here, right before the 3,000 mark, which tells me, I remember hearing a lot about that with carbon-hydrogen bonding. So that was what, single bonds, so that was what I ended up classifying that as. And then the last thing that I noticed was that there were aromatic CC bands between 1,600 and 1,490, so 1,600, so these two here. And so then that kind of clued me in to be like, oh, I might be dealing with an aromatic ring here. So that was a nice little clue. And then again, I kind of squirreled that away for later and moved on to the carbon NMR. So with this one, we can first notice that we have 4 distinct carbon environments within the aromatic ring range. So I classified all 4 of these as aromatic carbons, distinct aromatic carbons. And since I was already kind of on I'm working on an aromatic ring train, that told me that there was some symmetry going on. So there's 4 distinct out of the 6 carbons in a ring. This next one that I looked at, I'm like, what, the 58? Yeah. This one I called a CO bond. And downfield a little bit more, we got at the 32, I called that a carbon-hydrogen bond, and the 22, I called CH3 bonds, so methyl groups. Then moving on to the hydrogen NMR, the first thing that I kind of noticed was, again, some characteristic aromatic hydrogens. So all 4 of these here, both of these doublets, I classified as aromatic hydrogens, and that also points to symmetry again in our aromatic ring. This really tall singlet here is characteristic of a a methoxy groups. So that was what I ended up calling that one. This one here was interesting. I ended up counting it, and I think it was a septet, which tells me that it has 6 adjacent non-equivalent protons. And then lastly, this doublet here, the last 6 hydrogens, I classified as methyl groups. And I also at this point got kind of clued in that there's 6 hydrogens here in methyl groups, and that this septet next to it, if we're using the n+1 rule, it again would have the 6 adjacent non-equivalent protons. So I was like, okay, those two are probably going to be bonded to each other. So this is kind of the point where I started to throw together my structure. So I knew I had an aromatic ring. I knew I had multiple methyl groups. And I knew I had like a isobutyl group because of that, the 6 adjacent carbons there, or hydrogens. I knew that I had the CO bond going on. And so yeah, this is what I ended up coming up with. I made it on MolView, and it cleaned it up for me a little bit when I used like the cleanup button, which was cool. But this is the best I could come up with. I tried, and yeah. So thank you. Again, this has been my combined Spectra problem. I had prompt Y. My name is Molly Meager, and thank you.